Okay, so because it's a small group, I won't formalize this. So we have Vikram Krishnamurthy today. He's working in a startup company at near Georgia Tech in Georgia, and he has a varied experience in the wireless device semiconductor industry. So he's going to give us a talk on amplifier design.
Basically, I'll start off with just a little bit of an introduction for categorization of power amplifiers, and talk just a little bit about the wireless standard, and predominantly the standards that we were focusing on at National. Talk about some of the device technologies, the detailed design issues, some of the results we've gotten for silicon-based power amplifiers, and then the current research that's going on now. And if there is interest, I put some slides on for some other power amplifier work that was done, but that was done at V-band, so might not be as relevant, but might be interesting in terms of, I was talking with one of the professors about spatial power combining, so spatial power combining for cross-link satellite communications. But we'll stick to this, and then please feel free to ask any questions you may have. So primarily the two categories are the linear and nonlinear area, and really right now most of the attention is being attracted towards the linear PA area, primarily because of the database applications. And it really makes it very difficult in terms of the design issues, whereas the nonlinear aspect PAs, primarily you can have the power amplifiers operating significantly above their 1 dB compression points, and they can be relatively efficient, and that's not as important a factor. Whereas in the linear PA, you do have to be backed off significantly, and a lot of these waveforms, such as CDMA, have peak to average ratios on the order of 5 dB or so. So you have a trade-off between linearity. You have a large peak to average ratios, and you really have to get good efficiency. So it really makes it very difficult. And right now, the dominant products are in gallium arsenide to meet these requirements, primarily because those the devices that are used for gallium arsenide, primarily the HBTs, operate on a substrate which is semi-insulating, which can have very good efficiency. But nevertheless, there's been a lot of advancements in silicon device technology, and looking at silicon PAs, there's definitely potential in the, at least I would say, in the 2 gigahertz and below band. And I'll talk about especially one of the technologies, which is the silicon germanium bi-CMOS process. But at National, primarily, the areas we focused on was in the nonlinear PA area, and I'm going to talk mostly about that. And it really goes to explain a lot about power amplifier design and what the issues are, and can translate across this boundary. And one of the areas was in the cordless. It turns out that the largest commercial silicon power amplifier market is for cordless, and there are 2 standards in Europe and the US, and DECT is at 1.9 gigahertz and DCT is at 2.4. DCT is in the US and DECT is in Europe, and it's a constant envelope modulation scheme, so you can operate this relatively high into compression for the power amplifier, and the access is TDMA. So just the overall, just rough specs, and there's like a lot of detailed specs, especially in integrating a component into a system such as a handset. I just wanted to highlight just a few of the specs, but whenever you have to deal with a component and integrating that, it takes many months for even an evaluation of the product, of the PA, and integrating that in. And we're looking here just the overall top level idea is 26 dBm output power, and you really want to relieve pressure on the preamp that's on, primarily because that's integrated into the transceiver. And the preamp is coming off differential, and it's really very difficult even to get 0 dBm out of that transceiver chip. A lot of issues involved, and that's a CMOS chip coming out. So it really puts a lot of pressure on the PA end to try to be able to meet power gain numbers and of course power. The other trend is supply voltage variation, or trying to go to lower and lower supply voltages and have unregulated power. So especially in the cordless handset area, the trend is towards from 3.3 all the way down to 2.4. And so one really has to have flexibility in designing a power amplifier that has the ability to operate and meet some of these specs all the way down to 2.4 volts as well. And that really impacts the ability, the swing that you have for the PA, and really impacts the design in terms of the output power that you can get, considering that your efficiency is inherently limited for the type of operation, which would be Class AB. National was the #2 supplier of baseband and RF transceivers, so they really wanted to have a big effort towards integrating a silicon PA onto their chipset, not necessarily onto the transceiver, which would be the next step, quite a challenge as a 1/4 micron CMOS. And again, we're trying to be very sensitive to try to make sure that they can relieve pressure on the design of their driver to go down below 0 dBm, even though they could spec at 2 dBm on the driver coming out. The thought was to have very good power gain on the PA at 26 dBm, and try to look at a CMOS and a bi-CMOS process. And these were the names of the products that National has in both of those bands. And so predominantly the technologies, the dominant technology is gallium arsenide. I guess a little bit of history. I guess it turned out that the government had a long effort in gallium arsenide, long research effort, and TRW developed the first, one of the first commercial HBT processes, or military HBT processes. And there was this small company in North Carolina. They were called RFMD, and they paid $1 million to TRW, and they got this HBT process, and that was this aluminum gallium arsenide process, and the rest is history in terms of their domination of power amplifiers, especially for the cellular market. The advantage of semi-insulating substrate, that took a really long time to happen, and I think people stumbled upon it by accident. But now that semi-insulating substrates, very high mobility, and the device itself, very high breakdown voltages for the HBT, which would be the collector, the emitter breakdown voltage, and which is called BDCEO and BDCBO collector device. And what they do is this technology called heterojunction bipolar technology, which is basically a bipolar device, and they have a emitter which has a relatively higher band gap and allows for one to have very high betas on the device, and allows one to dope the base very heavily so that it can handle very, very high currents. And so it's a very, very really, really good technology. And in the silicon area, for a long time there wasn't an HBT technology, and one of the issues is it's a conductive substrate, and the mobilities are relatively lower. But of course the advantages are the high level of integration with CMOS. And it turned out that, I don't know, about 10 years ago or something, the silicon germanium silicon heterojunction was refined, and so what people decided to do there was use a silicon germanium base. So what you would have is a lower band gap than silicon, and you could see the percentage of germanium in the excuse me, the percentage of germanium in the base, giving you the 7 millivolt decrease, and it's about 4% grading in the base. And So that also gives you relatively high betas, but what you have really good is that the thermal conductivity of silicon compared to gallium arsenide is much better. So that gives you the good thermal performance. And you can do a lot of neat things with silicon germanium, the profile in the base, and you can help those electrons along in the base if you want to. It turns out that even though in terms of breakdown it's not compatible, but in terms of high current technology and the ability to have high SFTs, it really is remarkable improvements in the past few years for silicon germanium. So I think I said the high gain, and I discussed, the fact that what they do is for the silicon germanium, you create you have a valence band offset. So what happens is that you have the holes in the base of the device, and they have a tough time getting back to the emitter to recombine. So as a result, your beta, your collector current over your base current is very high, and then you can take the base and then you can make it very, very low resistivity, and you can get lots of current going through it as well. And if you do some neat things to the collector, you can have a trade-off between the F sub t, where the current gain goes to 1, the frequency with the current gain goes to 1, versus breakdown. And by varying the collector implant, you can either get a high F sub t device or a high breakdown device. And there's a lot of work going on, or currently going on, even at National, to try to optimize that to get a power amplifier process. Emitter lengths right now, emitter widths of about 0.35 to 0.5 micron devices. And this is the BVCEO, the collector to emitter breakdown voltage with the base open, which is not necessarily exactly the RF operation, but it's a figure of merit, looking at about 6 volts and an F sub t of greater than 25 gigahertz, which is really great, which might give you a good operation above 2 to 3 gigahertz or so. And number of foundries right now that have silicon germanium. Nationals come up, when I was there, we developed something there. IBM, really the pioneers, very, very impressive process. Jazz Semiconductor, which is a spin-off from Connexent, which is now Skyworks, which is Connexent Alpha. And TSMC is coming online with a process as well. So it really has, and then they have more robust types of devices. Like I said, you can have the trade-off between the high-speed F sub t or high breakdown type device. And so a lot of the issues with the silicon power amplifier, primarily the substrate parasitics, primarily any metal trace that you have, obviously you don't have a ground return. And so you don't, well, you do have a ground return, but it's the substrate. So as a result, you're going to be generating, anytime you have fields generated penetrating into that conductive substrate, you're going to have eddy currents that are generated, and that really is an issue. And then also, bipolar devices, inherently, the history of them, they're not very stable with temperature, so you have to do some things to make them thermally stable. And since power amplifiers are not as efficient, there's a lot of that power that goes into heat. You really have to think about ballasting, and I won't bore you with the details of, well, I mean, just basically, how current flows in a device, and sometimes current does not flow uniformly through a device, and as a result, some heating issues occur, and one has to do emitter or base ballasting. And then the thermal resistance of the package, that's really a big deal. You need a package with a metal plug, and if you just do a steady state 1D thermal analysis, you'll get an idea that you can't make it happen without a metal slug. And of course, the ground and package parasitics are very, very significant, especially when you're putting out that much power. You have a lot of inductances for the on-chip lines, and of course the wire bond and package parasitics, which have to be modeled very accurately in order for you to design. And it's more sensitive depending on the design topology that you're using. I mean, one type of topology, whether it's single-ended or a differential topology, which might offset the impact of the parasitics on your your device, on your PA performance. And then, of course, there's a bunch of acronyms here, and so GP is Gummel-Poon, so that was an old model that folks came up with for just pretty good for low currents, but with the relatively new types of device sizes and technologies, it's probably not as accurate and helpful at the high currents. So then these guys, I don't know, a bunch of companies got together and they call it the Vertical Bipolar Intercompany Model, VBIC. So they put together this, a more accurate model that really takes into account some more high current effects that are going on, base push-out effects due to at high current flows. But still, and then there's I don't know the acronym for ICOM, but that's yet another high current model. And what happens is that you have large devices, and they don't behave like a small device, and therefore you have issues with scaling, and then these things heat up just by themselves, and that's an issue. And then there's breakdown phenomena that has to be modeled. So it's really a very challenging area, I guess. Yes.
Why do you need the metal slug at the silicon and don't need it at the gallium arsenide? Shouldn't that be, if you have a high efficient device, shouldn't it be cooler than the other?
Yeah, no, it's not. Silicon right now is not as highly efficient, but yeah, even gallium arsenide also uses. Gallium arsenide has a relatively higher thermal resistance for its substrate, and they also use a metal slug. So gallium arsenide is efficient, but not as good of a thermal conductor. So they use a metal slug for their packages as well, and also to help with grounding. And for silicon, you're not as efficient, and you absolutely need it. So, so the whole. I have a slide on the temperature rise, and I'll show you the heat flow and stuff. But there's a lot of people. You could do all sorts of neat thermal modeling also. You're interested on that stuff. So. The topology chosen was looking at a common emitter three-stage design with trying to implement some type of novel power control on the PA, looking at a class AB operation. Principally, the issue with the supply voltage is very significant, and one has to really think very much about the type of analog circuitry needed to bias the device up. And so we did think a little bit about that. And shaping of the waveform is very critical in the power amplifier, and having a lot of second harmonics, would really cause unnecessary peaking of the fundamental waveform, and as a result, it causes a lot of efficiency hits and add an external trap to get rid of that. So it turns out that if you just look at the standard equations for collector current versus base emitter voltage, and you plot that, you'll see that you'll reach a point where on the current versus voltage scale, it'll start folding back on itself, and then you have a situation where you have decrease in base emitter voltage, but yet the collector current is still going up. So that's not a good thing. And you have, inherently, see how to explain. Inherently, one of the ways to counteract that is to add a resistance. And you can either ballast the emitter or ballast the base. And ballasting the emitter causes some issues in terms of the collector to emitter voltage swing is significantly reduced, not significantly, somewhat reduced, and thereby you might take a little bit of an efficiency hit. And for IBM's technology, if you're ballasting with an aggregate resistance of 1.5 ohms, it turns out that from the simulations, And also from measurements that 1.5 ohms would be sufficient to prevent thermal runaway. So the package is was a LLP16 leadless package, and then you can see the metal slug in the center, and didn't have it. Not sure how accurate the models are, but they did it's very hard to get numbers in this range. 6.9 milliohms, femtofarads for the parasitic capacitance. It's pretty low, which is good. It's still a bit difficult. Probably very good for us in terms of having stability for an amplifier, primarily because a lot of this creates unnecessary feedback, which you haven't compensated for, and then you end up with an oscillator. So you have to be very careful about that. Spend a lot of time looking at wire bonds, and turns out there is a significant amount of resistance relative to what we're to our interest in power amplifiers, especially at 2.5 gigahertz, about 160 milliohms, and your wire length about 1 millimeter. You're looking about a nanohenry, and then also you'd have to take into account the mutual inductance issues, and so you just can't use massive amount of wire bonds to solve your problem. One really has to think about that, and that's why having the metal slugs is very useful. You can have a down bond there. It can be a thermal and an electrical ground, and that really can reduce your ground inductance, which is very important. One of the ways to prevent a second harmonic from happening, or to trap the second harmonic, is to use a quarter wavelength at fundamental, and that's still very difficult to do. So we tried to institute some components over here as a trap. This is the output of the PA, and then there's the third stage supply coming in. So that's where the power is coming in. So one has to be very accurate at modeling every little detail to really understand what's going on, especially if you want to get waveforms that are meaningful in terms of being acceptable, in terms of harmonics, and also acceptable in terms of efficiency. And that's why we're interested in that. But of course, getting a feed through of the third harmonics would be good, because that would square out a little bit of the waveform. And if you square out that waveform, then what happens in that case is the overlap between the current and the voltage will be minimal at the collector node, and then you might have better efficiency. And since this is a nonlinear power amplifier, we like odd harmonics to go through. Don't like the even harmonics. So we did a lot more detailed thermal analysis. This is just steady state, and then we also did it's a TDMA system, so we did some time-dependent measurements as well. Sorry, not measurements, simulations as well. And I think you can see that the metal slug really is the path, especially with plastic encapsulation. Just looking at steady state, we're looking at the temperature rising to about 51 C, which is pretty reasonable for, and about 45 C for both of our cordless types of designs. Like for GSM, this is also TDMA. GSM is TDMA also, and one really has to be very careful and understand what the heat capacity is, and do some more detailed electrical equivalent modeling of, like, for example, an RC system, to really understand what the temperature rise and fall is for the type of TDMA signal that GSM would require. So this is a worst case analysis, just so that we can understand. And then you still have specs on top of it. This is at room temperature, so you have to go from room temperature from 25 to 85 C. So if you're at 85 C and you've got a 25 degree rise, you're at 110. So you're that's getting to be a problem. You might have some issues with especially with the device being able to put out that type of power at 110 C. And also the device failing, so there's really a lot of issues here, very, very important issues. And get very detailed into that, I mean, you have to assume that your board is a infinite heat sink, and it really isn't. Your board heats up also. So if you really want to do some accurate modeling, you'd have to do a little bit of computational fluid dynamics and assume that you have free convection across the board, and then you could see what the board heats up to, because that's the. Now, to be more detailed into it.
Excuse me. Do your conclusions take into account that the GSM system, for example, you have a duty cycle?
Yes, exactly. So we have the duty cycle in GSM, and I didn't bring the slides. We did the analysis. And that's where we take into account the heat capacity of silicon in these materials, and pulse it, and take a look at what the temperature rise is as an equivalent RC type circuit. But this was a steady state worst case situation, and it's 25 rise already, so it's very worrisome at 85C, because you have to pass specs at 85C, which would put you at 110, and GSM would be somewhat similar. Well, GSM is a different story. I'll talk about that a little bit later. Grounding is very, very important. Solder attach and ground parasitics. So this is an X-ray result of solder attach, and the type of current flow and how current flows from the ground paddle to the board is very, very critical, and how you have your ground vias, and we ended up using a lot more vias, would determine your constriction type of inductance, and is a very critical parameter, and also very, very important to get the type of solder coverage you needed in order to have really good grounding for power amplifier. Oh, and if it's really bad, and you can have, possibly hundreds of picohenries of ground parasitics, very bad things can happen. And this is a graph showing some of the bad things that can happen. And basically, you can really have a gain. You can have a drop in the gain, power gain as well as power, and one really has to be very critical. This was an ADS large signal simulation of board ground inductance, and you could see 120 to 360 picohenries. And this is just one stage, final stage gain, and then power. And input power, gain and power here. Apologize for not labeling the axes. So basically, you're looking at drops in. You can see significant drops in power as well as power gain, with having significant amounts of board ground inductance. One of the layouts. Did a lot of stuff, but basically showing you that there's a large number of grounds that are used, very critical, and using the down bonds are very, very important. And the layout itself can have a significant impact. There's a lot of art involved in doing the layout and understanding what the detailed parasitics are and how each device behaves differently, because not everything's in a symmetric environment, and one really has to think about how to design in that. I think it's a very, very critical area. The Loadpull is basically a means for testing the power amplifier, and basically most of this is done by having tuners at the input and the output, and you need a lot of things to. These days, now they have automated tuners, and these tuners can help you match your output and your input. You can see the fundamental source tuner here, and then you can see the load and the pre-match fundamental tuner there. And you have a pre-match and a fundamental tuner primarily because your output impedance is so low that you need to match that to 50 ohms. You need two tuners back to back in order to get that type of visual range for that. And then, if you can, you have a harmonic load tuner to help you with tuning the second and third harmonics off of a triplexer coming off of there. So this was a setup. Excuse me. This is what the sample looks like. seen these with board. I use the G-Tech board, a little bit lower loss tangent. At this frequency, it's probably not as much concern. Conductor loss is predominant here. But in any case, similar type of setups with boards and a chip there with external passive components. So here's the results of the 2103, which was at 2.4 gig. And we had about 28.8 dBm of power at 3.3 volts over there, and then you could see that output power versus supply, and we come down to about 23.2. And Philips and Infineon, these are all competitive silicon PAs. A little bit of an over-design at 3.3, a little bit more output power than is needed, so that needs to be a little bit fine-tuned. But it looks pretty good in terms of power numbers, up to about 2.2 volts. The bottom drops out at 2.0, a very, very tough design. Consider, so you've got some good range from 2.2 up to about 3.3 volts, comparing with the Infineon 6823. And looks pretty good, reasonable in terms of efficiency. Philips looks good, but it's at 1.9 gigahertz. They've got 40%. Again, the flagship Infineon 6823 were pretty comparable on where they are. Their differential off 2 to 3 dBm input power, so their power gain is slightly degraded compared to ours. So that's to be expected for differential design. But nevertheless, this is reasonably comparable. And the harmonics, so we said it's important to have a 2F0 trap, especially for a single-ended design. And so basically, looks pretty good looks pretty good even at 2.0. So it's pretty comparable again at 6823. So that was a pleasant surprise, especially for a single-ended design, to get those types of harmonics. So basically, the summary of the nonlinear PA area we're looking at is really good output power from 2.2 to 3 volts, comparable with what other guys have. And it's really important from a system perspective that, you know, it's not only the PA, but what goes after it, especially all the filtering, that really gives you an aggregate efficiency that's somewhat lower or significantly lower than what people tout as the PA efficiency, and that's what the system folks are primarily concerned about. And that's why, you know, 2F0 filtering, it can be relaxed, in this case, primarily because there's so much margin, and I told you we're at minus 30 dBc on the requirements. We also did designs in a 1/4 micron CMOS, but didn't get a chance at that stage to do the measurements as well, and that's a very, very challenging area, especially with a highly conductive substrate that's used for CMOS. We did a little bit of work on GSM, and we did have triple band designs, and right now the GSM standard is a quad band. 800, 900, 1800, and 1900. And you guys know all of this. So they're looking for 35 dBm output power, 30 dB gain, minus 45 dBc harmonics. And so it's a very, very challenging problem. And we got some results. Didn't meet the power requirements. It was a 3.2 volt operation. We had spec requirement that we had to drop the supply voltage down to that level. Output power about 33.5 dBm, efficiency of about 50%. It's pretty good. Certainly would have liked another crack at this, but very promising results, especially for nonlinear power amplifiers with silicon, considering all of the problems, all of the parasitic issues that silicon has. Okay, and then we were also involved in doing Bluetooth power amplifiers. This is a 2-stage PA for class 1 at 2.4, and the two other companies involved were SiGe Semiconductor and Maxim. And at 3.0, we're sort of in the ballpark there with what those guys have, and this is the chart of input power versus output power and efficiency, so everything's sort of all put together here, and you can see the numbers below. Looking at, you know, right now it's still a question whether people want to use class 1. You know, I don't know. You know, it's not that hot. People are interested in class 0 and want to integrate everything onto a single chip. So you know, there's a lot of market risk, but nevertheless, it's very promising for Class 1 if that takes off in the market. So, you know, I really believe, you know, from what we've done, that silicon germanium, it really is a viable solution for nonlinear PAs. And like I told you, even at National, we've developed a process there for HBT devices with high breakdown voltages. You need that swing. And the substrate parasitics, you know, you could see really can have an effect, and one would have to think about potential differential PA with a balun. And then, yes?
Would you please go back one slide? So P out is like 21 dBm.
Yeah.
So it's like a bit more than 100 milliwatts.
Yeah.
Is it looking too much for Bluetooth?
Class 1, that's what Class 1 specs. Class 0 is very small. Class 1...
Class 1 is 20 dBm?
Yeah, Class 1 I think is
No,
20.
usually the operational point is smaller than that.
Yeah, but you lose, I mean, that's the output of the amplifier. You lose that some matching filter.
Right.
The total output will be fine.
Would be
Below 20.
Exactly. So we had to design for what all these other guys had, so we tried to match those specs for SiGe and Maxim. You know, this is a little bit harder problem. Differential PA, one has to be very creative in designing a high-power balun, or being creative about it. There are companies out there and places, universities that have done some interesting research on differential PAs and balance, and I really think there's a lot of room there for creativity. And of course, this really opens up the road for a lot of research on integrating the PA with the rest of the radio, which has a million issues. But nevertheless, by doing it in silicon, you really set yourself on a foundation, the first step where you can move forward and try to do something. So the current research I'm working on at VT Silicon is on linear PAs. And so you guys know all this stuff, and basically there's like a bunch of 2001X standards, you know. There's a 153 kilobit standard now, and then there's going to be a 300 kilobit standard, and so you can see the data rates are going up. So right now, you guys know all this stuff. CDMA 2000 has 50% of the market in the U.S. right now, so it's pretty dominant. And we're trying to look at, you know, how can you develop PAs, especially for this quote-unquote 3G type of migration. And there are spec differences between CDMA 2000 and wideband CDMA. Wideband CDMA, I think, you know, currently 5 megahertz channel. I don't know what it is in Korea. I don't know the Korean standards. I think it's 5 megahertz in Korea, Japan. So basically, two sort of paths that'll merge together. And what we're trying to do is develop a silicon-based power amplifier for the CDMA 2000 and wideband CDMA market. And it's a linear power amplifier. And like I said, the peak to average ratio that you're looking at for for IS-95 is 3.9, but the CDMA waveform technically is 5 dB, 5.1, 5.2 dB peak to average ratio. So the back off is quite significant. Since you have such significant back off and very, very stringent requirements on ACPR, specs on the order of minus 45 dBc. What that really does is the statement here by Sony that your PA is going to suck a huge amount of power, and you really need to do a lot of processing on the baseband. And I think that really makes it very difficult. You can't really have a handset that needs to be charged every half an hour or so. You know, I think you really, and that seems to be one of the factors. And size, of course, with the additional features, and therefore. The reason why that statement at the bottom is necessary in order to really make this a viable technology for 3G. Because the power distribution is on a Gaussian distribution, the probability distribution function one gets an average for the distribution for the urban and suburban environments, and comes up with an average urban and suburban current consumption for the cellular environment. And we use that, and the handset manufacturers use this rather than just peak power efficiency, because you're not at peak power all the time, and especially for CDMA, you're backed off maybe 15, 20 dB, the peak of that distribution. And again, that is, again, we're only talking for voice-only applications, for data applications, again, because of the fact that you may have much more stringent linearity requirements, that distribution may be shifted up significantly in power by like 4 or 5 dB, and that can cause your average urban and suburban current to shoot up for database applications. Linearity. And the other thing is, a lot of people don't, silicon inherently has some issues with a VSWR issue, which is the antenna mismatch. And, you have to handle a mismatch and still meet linearity, and currently there are requirements where you cannot use an isolator. An isolator is a ferrite component that, provides you with a 50 ohm input impedance regardless of what the output impedance is. So the antenna can see all sorts of different environments. So what this means basically is, if I'm Verizon and I'm testing Nokia's handset versus a standard in New York City or something, and I'm on a call and I take the handset and I put it on top of a car, which has a metal top, I can't drop the call. I can't, and that's a test. And so in order for us to make sure that these guys, Nokia, is happy with the tests that's going to happen with Verizon or Sprint, ruggedness is very critical, and trying to eliminate the isolator, it's a very, very difficult problem. Very difficult problem to try to do, and right now that's what we're working on. We certainly have quite a few ideas on how to do that.
Excuse me, I have a question here. You just mentioned that voice and data traffic will have like different peak to average statistics.
No, the average urban and suburban current, the probability distribution function versus power, will shift upward because of the fact that one will have to transmit at relatively higher powers in order to have a relatively low bit error rate at these high data rates. So the voice, which is vocoded at 9.6 kilobits per second, the requirements for voice are significantly different, and so the distribution, right, versus power will be centered. I'm going to say, I don't have the distribution on me, but I'll say it's at 5 dBm or so. Maybe not. Maybe it's 2 or 3 dBm.
So pretty much, in simple words,
yes.
The data traffic will just require high power.
Yes, yes, exactly. And that's well, that's right. Okay, so our current research is looking at an intelligent or smart silicon power amplifier, and basically that combines power management and an isolator right now. Not an isolator, eliminates the isolator, and that function is integrated into intelligence in the silicon. And predominantly we're looking at various types of current control mechanisms, potential analog circuitry and digital circuitry in terms of a DC to DC converter. A lot of people have done it off chip, and there are many different types of converters and all sorts of thoughts of how to do that, and I won't bore you with that stuff. So there's many types of converters. There's in the digital world, there's linear converters, and then in more the analog realm, one that's interested in a buck converter that can really, the linear converters have very poor efficiencies, and we want relatively high efficiencies, and so therefore the DC to DC converter to be able to control the supply voltage is one thought, or there might be other means of doing that as well. And intelligent analog and digital circuitry, a lot of analog and digital blocks needed to do VSWR detection and control, and that's what I'm working on. And trying to come up with some alternative PA architectures. And this is our estimate. Certainly changes. So looking at looking at the PA, you're looking at maybe 300 milliamps of power consumption. It really depends on the baseband and what type of processing you're doing. So you really, it's hard to put a metric on this, or to have a standard on it. And really looking at the smart silicon power amplifier, we can increase the battery life by roughly about 18% at high data rate transmissions. And either you can do that, increase the battery life, or free up more power consumption for the baseband, so that you can essentially have more time for processing photos or videos or whatever you guys are transmitting. And so that's pretty much a summary.
When the CDMA 2001X standard was first adopted in '99, one of the selling speech was that compared to IS-95, it doesn't need to change anything in the analog portion, except for there was some filter tuning to bump out the signal to noise ratio. But all amplifiers, mixers, just everything is that's what makes it cheaper. What exactly?
No, that's true. That's true. We're trying to fit, no. When we talk to Nokia or Sony Ericsson, we have to fit the form factors for that PA. But, you really have to see that, there's really an issue with battery life, You can't have people, you can't have some data transmission and all of a sudden you're back to charging your battery. It's not a viable product. And so something has to be done. But I know talking to these guys, there's stringent requirements on size. You can't do crazy things. And that's why we're trying to fit everything onto a 4x4 or 5x5 millimeter packaged part. And it's very, very difficult.
So what you're saying is you can use the IS-95 analog part for CDMA 2000, but then you will have very short battery life. That's what you're trying to say.
Exactly. And it's, there's, I don't know. But IS-95, then you've got all sorts of issues. I don't know. You've got system capacity arguments at, Yeah, okay, you're right. You're right. A lot of the system capacity arguments can be handled by a lot of the turbo coating on the forward link, even into the handset as well, to give you capacity improvements. But the IS-95, there's also, yeah, you're right. We're essentially trying to keep it very similar on the RF end, but it's still not viable. It's not a viable solution, especially at very high data rates.
Stefan, the real problem is here that in IS-95, especially on the reverse, when you have just PPSK or PPSK modulation, you're pretty much at almost constant envelope. While when you go with a higher rate and you employ higher rate modulation, suddenly you get the peak to average issue much more pronounced than then you have to back off from your power amplifier more substantially, and then the efficiency of power amplifier just drops down.
Correct.
So even though theoretically it will work, but in reality, I would agree that the battery life will cut by at least factor of 2 more.
And I think it's probably more. It's evident in Korea and in Japan, especially with some of their 3G networks. I think it might be. And that's why Sony made those statements. And there's two ways to look at it. Either you can come up with neat technology for indium gallium phosphide, gallium arsenide types of technologies, very exotic technologies where you can try to do something with silicon. Right now, the majority of people are working on are the exotic gallium arsenide-based technologies. So I really think that because under 2 gigahertz, there really is a good chance for silicon to make inroads. And the only way to make those inroads is to take advantage of the type of intelligence and that you can come in, especially, and also with integrating additional functionality. Well, that's my view.
I have a question. There is now a lot of talk about so-called 4G stuff, and a lot of proposals are centered around the OFDM type system. It's like this plain frequency hopping OFDM and some variations of it. And in order OFDM, the peak to average is actually even much larger than that. So the people are talking about like 11, 12 dB. So how would it be? And there was a whole camp of people who were saying that this peak to average will actually make the system impractical because the power amplifier will be extremely efficient.
Well, okay, you have to think about it more on a, even in the CDMA realm, you have to think a frame on CDMA 2000 is 20 milliseconds, okay? I have to meet average ACPR over the frame, a lot of people tell me. So even in OFDM, the odds of me getting that high peak to average coming, I may have to sacrifice that high peak to average and try to meet my linearity over some length and hope that calculations come across. I can't, you know, that's intractable problem to be able to meet peak to average specifically for each of that. No.
Because actually the problem is that this 20 millisecond frame is actually a voice frame.
Yes.
So the Emitte 2000, the data frame of the small slot is actually 1.25 milliseconds.
Okay.
And in the wideband CDMA, even have that, it's 0.625. So it's even shorter. So and the OFDM operates on about the same
frame rate.
The same frame. So it means you have to meet much smoother.
That's true. Very true. But it's not all. But you know, I've been told that there's flexibility on number of frames also. So you know, it's a very difficult problem. I certainly don't have an answer for that in terms of.
But do you think the solution is this, or it's really something?
No, I think. You know, it depends on the data rate. You know, I mean, your bit error rate and your data rate. You know, as long as you're willing to compromise a little bit on that, sure, a solution exists. You know, at 5 gig for OFDM, I don't know if silicon is the answer yet. You know, for wideband CDMA, you know, and you give me a little bit of room on meeting for over a number of frames. You know, I might that might happen, but it's very hard dynamically to meet those types of requirements. And the testing is done, you know, I'm told by the people who do the testing that they're willing to give me some allowance for testing over multiple frames. So the question is, what is multiple to be able to do that? But, that's a good question. I mean, certainly some degree of give and take has to be done there. Hopefully I haven't bored. No one's sleeping, so that's good. All right.
Are you done?
Yeah.
Any other questions? So actually, I'm kind of interested in this question that what does it mean to do such a test? You just do a linearity measurement of some sort, which is dynamic over a given window, or I would imagine when you pass the signal through this, if you do it over a wider window, it will cause serious distortions at the instantaneous level. So who decides these kind of tests?
The handset, well, for us, it's the handset manufacturer that tells us over how many frames they're willing to take it, unless some system guys can, you know.
Well, it's really a system-dependent question. What I think he's contemplating is that if for a very short burst I violated the linearity and the Solde decisions which are being put in the decoder are truly correct, nevertheless, because the code is strong, still it might result in no errors.
Right.
It really depends on how the system. Usually the systems which have hybrid IQ, they are more tolerant towards this kind of stuff because at the worst case they just retransmit. And then there is of course the game of how short the frame should be.
Right.
Because if it's a very long frame, or if you count over a large number of frames, and then this whole block is being lost, then the whole block is supposed to be transmitted, which is added over here. So it's usually a kind of trade-off thing. One plays one way or another, and finally settles out for something which is acceptable.
And in a cellular environment, that's the peak data rate. So you won't I mean, you'll just, you know, your data rate goes up. You know, you're going to back down on that data rate. You know, right now it's 153, going up to 300. That's peak 300. So keep that in mind. It's not an average 300.
For the old ADV, it will be something like the peak is like 2.4 per second. For the wide density MA, I think it should be about 3 times as much.
So in the kind of modeling that you are doing for 3G, do you have a standard reference model for the channel including amplifier nonlinear?
For amplifier, from the analog portion, we usually just get the time jitter stuff. So the phase loop accuracy is being modeled, but trying to get the power amplifier shape into the simulation, not yet. But for the 4G system, like the ones which is RDM based, because power amplifier problem becomes actually much more severe than CDMA has something like 5 to 6 dB peak average, and that has 12 dB, which is like 6 dB more, 4 times more linear scale. And in that case, I'm thinking we will at some point we will put in maybe just so you know a curve of the amplifier response function. So we wouldn't model amplifier very detailed at this for now, but this will be a part of the laboratory study.
Okay, thank you.
Sure.
Thanks.